Let's say we have two lines over here. Let's call this line right over here line AB. So A and B both sit on this line. And let's say we have this other line over here, and we'll call this line CD. So it goes through point C, and it goes through point D, and it just keeps on going forever. And let's say that these lines both sit on the same plane. And in this case, the plane is our screen, or this little piece of paper that we're looking at right over here. And they never intersect. They never intersect. So they're on the same plane, but they never intersect each other. They never intersect. If those two things are true, then and they're not the same line, they never intersect, and they can be on the same plane, then we say that these lines are parallel. We say that they are parallel. They're moving in the same general direction. In fact, the exact same general direction. If we were looking at it from an algebraic point of view, we would say that they have the same slope, but they have different y-intercepts. They involve different points. If we drew our coordinate axis here, they would intersect that at a different point, but they would have the same exact slope. And what I want to do is think about how angles relate to parallel lines. So right over here, we have these two parallel lines. We can say that AB, line AB, is parallel to line CD, is parallel to line CD. Sometimes you'll see it specified on geometric drawings like this. They'll put a little arrow here to show that these two lines are parallel. And if you've already used the single arrow, they might put a double arrow to show that this line is parallel to that line right over there. Now, with that out of the way, what I want to do is draw a line that intersects both of these parallel lines. So here's a line that intersects both of them. Let me draw a little bit neater than that. So let me draw that line right over there. And I'll just call that line, well, actually, I'll do some points over here. Well, I'll just call that line L. And this line that intersects both of these parallel lines, we call that a transversal. This is a transversal line. It is transversing both of these parallel lines. This is a transversal. And what I want to think about is the angles that are formed and how they relate to each other, the angles that are formed at the intersection between this transversal line and the two parallel lines. So we could first of all start off with this angle right over here, that angle right over there, and we could call that angle, well, if we made some labels here, that would be D, this point, and then something else, but I'll just call it this angle right over here. We know that that's going to be equal to its vertical angles. So this angle is vertical with that one, so it's going to be equal to that angle right over there. We also know that this angle right over here is going to be equal to the angle that its vertical angle, or the angle that is opposite the intersection. So it's going to be equal to that. And sometimes you'll see it specified like this. We'll see a double angle mark like that. Or sometimes you'll see someone write this to show that these two are equal and these two are equal right over here. Now, the other thing we know is we can do the exact same exercise up here, that these two are going to be equal to each other, and these two are going to be equal to each other. They're all vertical angles. What's interesting here is thinking about the relationship between this angle right over here, the relationship between that angle right over there, and this angle right up over here. And if you just look at it, it is actually obvious what that relationship is, that they are going to be the same exact angle. That if you put a protractor here and measured it, you would get the exact same measure up here. And if I drew parallel lines, maybe I'll draw it straight left and right, and it might be a little bit more obvious. That if I draw it, so if I assume that these two lines are parallel, and I have a transversal here, what I'm saying is that this angle is going to be the exact same measure as that angle there. And to visualize that, just imagine tilting this line. And as you take different, so it looks like it's the case over there. If you take the line like this, and you look at it over here, it's clear that this is equal to this. And there's actually no proof for this. This is one of those things that are that a mathematician would say is intuitively obvious. That if you look at it, as you tilt this line, you would say that that these angles are the same. Or think about putting a protractor here to actually measure these angles. If you put a protractor here, you'd have one side of the angle at the 0 degree, and the other side would specify that point. And if you put the protractor over here, the exact same thing would happen. One side would be on this parallel line, and the other side would point at the exact same point. So given that, we know that not only is this side equivalent to this side, it is also equivalent to this side over here. And that tells us that that's also equivalent to that side over there. So all of these things in green are equivalent. And by the same exact argument, this side right over here is going, or this angle is going to have the same measure as this angle. And that's going to be the same as this angle because they are opposite. Now, or they're vertical angles. Now, the important thing to realize is just what we've deduced here. The vertical angles are equal, and the corresponding angles at the same points of intersection are also equal. And so that's a new word that I'm introducing right over here. This angle and this angle are corresponding. They represent kind of the top right corner in this example of where we intersected. Here they represent the, I guess, the top or the top right corner of the intersection. This would be the top left corner, top left corner. They're always going to be equal, corresponding angles. And once again, it comes really just, it's a, I guess for lack of a better word, it is a bit obvious. Now, on top of that, there are other words that people will see. We've essentially just proven that not only is this angle equivalent to this angle, but it's also equivalent to this angle right over here. And these two angles, maybe if I call this, let me label them so that we can make some headway here. So I'm going to use lowercase letters for the angles themselves. So let's call this lowercase a, lowercase b, lowercase c. So lowercase c for the angle, lowercase d, and then let me call this E, F, G, H. So we know from vertical angles that B is equal to C, but we also know that B is equal to F because they are corresponding angles. It's equal to F, and that F is equal to G. So vertical angles are equivalent, corresponding angles are equivalent, and so we also know obviously that B is equal to G. And so we say that alternate interior angles are equivalent. So you see that they're kind of on the interior of the intersection. They're between the two lines, but they're on all opposite sides of the transversal. Now you don't have to know that fancy word, alternate interior angles. You really just have to deduce this, what we just saw over here. Know that vertical angles are going to be equal and corresponding angles are going to be equal. And you see it with the other ones too. We know that A is going to be equal to D, which is going to be equal to H, which is going to be equal to E.